Okay, so Gloria, please start when you want.
Okay. Okay, so the exercise that we started yesterday that we are going to finish now is the calculation from the Chiral Lagrangian for mesons and baryons of this vertex here as sigma minus going to lambda pi minus. Okay, I'm showing here the full Chiral Lagrangian again that we started from. And we saw that we had these covariant derivatives here, and then we also had these terms here with this u mu that we had to expand in terms of the in order to see which terms we need to compute and get the vertex that we want, right? So for this term here with the covariant derivative, after expanding in the meson fields, we saw that we get this expression here. And I'm telling you that this term here will not contribute to the vertex that we want to compute. Did anyone try to compute it, or can anyone tell me why it will not contribute? You don't see why? Well, we see that in this vertex, we have an incoming baryon and an outgoing baryon and another outgoing meson. So we will need terms that have a B bar for this outgoing baryon, a B for this incoming baryon, and then meson field, phi. So we see that we don't have any of these terms here. This term only has a B bar and a B. It doesn't have the meson. And these terms here contribute to the scattering of baryon meson going to baryon meson, because we see we have the B bar, the B, and two mesons in all of these terms. So this cannot contribute to this vertex that we are interested in. So we have left two other terms, right? These ones that go with this u mu that we also expanded in terms of the meson fields. And we got these expressions here, okay? Where we have a B bar matrix, a B matrix, and one meson matrix. So these in principle should contribute to the vertex that we want to compute. So I will give you a few minutes to try to compute this first vertex, this first term here, okay, if you agree. If you can copy it, I will show you also the expressions that we got for these matrices for the vertex that we are interested in. I give you a few seconds to copy it, and then I will show you the matrices so you can get them also. Okay, so the matrices were these ones here, okay? For the incoming meson, we only keep the sigma minus in the matrix B. And for the B bar, we have to keep the outgoing meson, the lambda, in this case, a lambda bar, because it's here we have annihilation fields and we are creating a lambda, so we put the lambda bar. We saw yesterday that's what we have, the B bar matrix. And the meson matrix, we saw that we have to take this one here for the phi. Okay, so I give you a few minutes to compute the matrix products. If anyone gets to the solution, you can speak loud and tell me what you get.
Excuse me.
Yes.
Can you show the other slide again, please?
Yeah.
Thank you.
This one here.
Thank you.
Okay, so I show you here what I wanted you to do. We had this expression here, right? And we just substitute, we have this factor minus square root of 2 over f. Then we get this b bar that we saw that contains the lambda field, right? Then we have this mu, gamma mu and gamma 5 that we just keep here. And then we have the derivative of the meson field, and we only keep the pi minus in our vertex, okay? Then this we have to multiply it by the matrix with the incoming baryon, so the sigma minus here. And then because we had this anti-commutator, we have the inverse product, okay? So if we do these products here, okay, we have this B bar matrix here that we have to multiply by this. If we do these products, right, we see that in the first term we get this derivative of the baryonic field and multiply by the sigma field. And then here we get the opposite, but now we can apply the fact that the fields of mesons and baryons commute among themselves. This was not the case for meson fields multiplied by meson fields. We had, when we were taking the derivatives, we had to take into account that we had to take the derivative of the first field multiplied by the second field, and then the derivative of the second field multiplied by the first one. But when we have mesons and baryons, these fields commute, so these two terms are the same here, so we can take them out of the matrix. And we just get this here, okay? And next we have to take the trace of this, and this just gives us a factor of 2 here. So we see that these terms for this vertex gives us this expression, okay? And for the other term, we had instead of an anti-commutator, we had a commutator, right? So this will change as the sign that we have here. We'll have a minus sign here. So what will we get in that case? Can anyone tell me, just like directly, if you see what will we get? It's only a minus sign difference here. We will have that these products are the same, but we will have this a minus sign here. So this will give us here a minus sign in front of this element. So here we will have 1 for the first element, but a minus 1 here. So when we take the trace, this will give us what?
0.
Exactly. Exactly. We do this, we see that this term here doesn't contribute to this vertex, and it's not because we don't have the right amount of fields or anything. It's just because the coefficient is just a 0. When we take the trace, we get a 0. So we see that from the full Lagrangian that we had here, the only term that contributes to our vertex is this one here. We have calculated this trace, and we just have to multiply by this factor d over 2. And we get here the final expression that when we wanted to find. Okay, And what we can observe here, for example, is that a fact that pseudoscalar fields always enter in this kind of chiral Lagrangians with derivatives. And when you apply this derivative, this will give us a momentum. And the baryonic fields, we will just need to substitute by the proper Dirac spinors, and we will be able to compute the amplitude from this kind of Lagrangians. And this you can work out for any kind of process that you are interested in. And this is for this, we took the Lagrangian involving baryons and mesons. We can also take Lagrangians only involving mesons if we are only interested in studying mesons. So you see that this tool is quite powerful. Okay. Any questions about this exercise? I guess it's clear. So the next exercise that we are going to do is related on the equation of state of neutron stars that Laura was telling about in yesterday's lecture. And this is the exercise, okay? We consider a system of nucleons, only neutrons and protons, okay? And we take for the energy per particle of this system, we take a parametrization for this energy density, energy per particle, okay? And this, we see that Laura was telling us yesterday that there are usually two terms here, right? One which is more related to the compressibility, right? And the other one is is related to the symmetry energy. There is in this parametrization, we have this U here, which is the baryon density. In this case, baryon density is defined as the proton density plus the neutron density. And we take it dimensionless by dividing by this rho 0, which is the nuclear saturation density, which is 0.16 Fermi to the -3. Okay. And then we also have the proton fraction, which is just defined as the proton density divided by the total baryonic density. And we have also this parameter here, E0, which is the binding energy at saturation density, and it tells us that it's 15.8 MeVs. There are also two other parameters, the delta and the gamma, and they tell us also the value. And there is this asymmetry energy, which is 32 MeVs. Okay, and this is a very simple parameterization for the equation of state of nuclear matter, but it gives a good reproduction of equations of state that have been derived microscopically. And the parameters, these parameters that you see here and the values here have been fitted to reproduce nuclear properties like the saturation density, the binding energy, and the incompressibility modulus at saturation density. And if you are interested in reading more, this parameterization is given from this article here. Okay. So the first thing that they ask us is to calculate the energy density. We were given, okay, the energy per particle. What do we have to do to calculate the energy density? Energy per particle is the energy of a single nucleon, okay? The energy per nucleon. And what is the energy density? The energy density is energy divided by volume, okay? This the definition is energy, it's a density. So energy divided by volume instead of number of nucleons. So basically what we have to, if we want to compute energy divided by volume, we just divide by number of nucleons and multiply it also, and we see that we have this energy per particle, that is the expression that we are given here, okay, multiplied by number of nucleons divided by volume. What is this? This is the density, the baryonic density, okay, the nuclear density. So we just need to multiply the expression that we are given by the exercise times the nuclear density. And if we do that, we just get this here, okay? This is very easy to do. Okay, where I just changed where I had some U, which is density divided by saturation density. I substituted because I have density squared here, but divided by saturation density. And here I have density to the gamma plus 1 divided by saturation density to the gamma. Okay, so next they tell us to show that the chemical potential of the neutron and that the chemical potential of the proton are given by these expressions here. Does anyone remember from yesterday how we compute chemical potentials once we have the energy density?
A derivative with respect to the particle number.
Exactly. The corresponding chemical potential is just obtained by deriving the energy density by the corresponding density, right? So if we want the chemical potential of the neutron, we divide the energy density by we derive with respect to the neutron density. So we see that the expression that we derived before doesn't depend directly on the neutron density and the proton density, but on the total baryon density and the proton fraction. So we just apply partial derivatives, okay? So the derivative with respect to the neutron density is the derivative of respect to the total density, and the derivative of the density with respect of the neutron density, plus the derivative of the energy density with respect to the proton fraction, and the derivative of the proton fraction with respect, oh, sure, sorry, this should be a neutron here, with respect to the neutron density here, okay? And the same for the proton, when we take the derivatives with respect to the proton density. So we see that we need to compute the derivatives of the density and of the proton fraction with respect to the neutron and the proton densities, okay? I give you 5 minutes to do that maybe, so you can try to do it yourselves. I show you again this expression here, and if you remember, the total density is just the sum of the two densities, and the proton fraction is the proton density divided by the total density. Okay, so what is it? The derivative of the baryonic density with respect of the neutron and proton density, this is just 1. And for the proton fraction, as I said, it's the proton density divided by the total density. So it's minus the derivative with respect to the neutron density is minus the proton density divided by the total density, and this is just proton fraction divided by density. And the derivative with respect to the proton density, this gives us 1 minus the proton fraction divided by the density. Okay, but we also need the derivatives of the energy density with respect to the density and the proton fraction. We already obtained the energy density in the first exercise, okay? And where we have a U, we know that it's the density divided by the saturation density. So what do we have? We have that the derivative of the energy density with respect to the density, and the energy density is nothing else but the density by the energy per particle. This is the energy per particle plus the density times the derivative of the energy density with respect to density. Of the energy per particle, sorry, divided by energy, which is the exercise is giving us the energy per particle. And for the proton fraction, the derivative is just the density times the derivative of the energy per particle divided by the proton fraction. So we just applied these derivatives of the to the expression that we were given in the exercise, okay? These are quite some long derivatives, but they are straightforward derivatives, okay? So the derivative of the energy per particle with respect to the energy density, because the expression that we are given depends on U. We do the derivative with respect to U, and we get these expressions here, okay? You can try to do it yourself and you'll see that you should get these expressions here. Okay. So finally, we substitute everything in the expressions for the chemical potentials that we obtained a couple of slides ago. And we work out the algebra. So we have for the neutron chemical potential, we have the energy per particle plus the density times the derivative of the energy per particle divided by with respect to the density, minus the proton fraction times the derivative of the energy per particle with respect to the proton fraction. And if we substitute, we have the expression that we are giving for the energy per particle right here, plus the density times the derivative of with respect to density, plus the proton fraction. Okay, so if you sum up everything, you will get this expression here for the neutron chemical potential. And if you do the same for the chemical potential of the proton, you'll see that the expression is very similar. Okay. Basically, the difference is that here you have 4 times the proton fraction, and here you have minus 4 times 1 minus the proton fraction. So you can say, okay, what is the difference between the neutron chemical potential and the proton chemical potential? This we will need it later if we just do one minus the other one. We will just get this term here times this factor here, the symmetry energy at saturation density times U to the gamma 1 minus this -4 and 1 minus 2 proton fraction. Okay, if you remember these expressions here, we will need them later on in this exercise. Okay. So the next that we are asked to do is to calculate the pressure, the total pressure of the system formed by protons and neutrons. Okay, and get this expression here. How can we calculate the pressure? Do you remember the expression to calculate the pressure? There are in fact two options. We can do it in two different ways. First way we can do that is applying this expression that we saw in the lectures yesterday. The pressure is defined as the density to the square times the derivative of the energy per particle with respect to the density. Okay, and we are given this expression, so it's again deriving these expressions here, and we can obtain the pressure. Okay. I give you a few minutes to do so, maybe. So you can try to work out these kind of derivatives yourselves. So did you get this expression here? Or do you have any trouble? It's quite straightforward, right? If you just apply this expression here, you should get what we are given by the exercise for the pressure. Okay. You should rewrite a bit until in the end we get this here. Okay, so I told you there are two ways. One is just applying this definition for the pressure in terms of the derivative with respect to the density. What is the other way? Well, if we remember also from yesterday, we saw that we can define, we can rewrite this derivative of the energy per particle with respect to the density in the definition of the pressure, using the fact that the energy density is the energy per particle times the density. So if we do this, we take the definition, okay, the density to the square times the derivative of the energy per particle with respect to the density. We said that we substitute here the definition, the energy per particle is the energy density divided by density. And if we take the derivative now, we get derivative squared divided by the derivative by the density. Okay, so we just get one density here times the derivative of the energy density with respect to density, minus, because if we take the derivative with respect to 1 over density, this is minus 1 over density squared. That cancels with this density squared here, and we just get minus the energy density here. Okay. And what was this? Okay, this we can rewrite it as the sum of the partial of the derivatives with respect to the partial densities. Okay, here. And what was this here? We just seen in the previous question that this is the definition of the chemical potential. The derivative of the energy density with respect to the density of a certain particle is its chemical potential. So the pressure can be just calculated as minus the energy density plus the sum of all the chemical potentials times the partial densities. Okay, and we already calculated the chemical potentials in the previous exercise by taking these derivatives. So we can just substitute this to calculate the pressure, and we should get the same expression. Okay. So if we do that, we get this expression here. Okay. We substitute the energy per particle here. Okay. Then the first term of the chemical potential times these densities here that I'm summing because it was the same expression for both. And for the other term, we saw that they were very similar, but there was a slight difference, right? So this term was common for both. So we get also the sum for times the sum of the neutron density and proton density, but there was an additional term for the neutron chemical potential and proton chemical potential that were different. So we have these two terms here and this other term with the mass. Okay. And if we work out a bit to rewrite it, we can write it again as the expression that is given for the pressure in the exercise. And we just get this here again. Okay. Any questions? Okay, it's just some easy computation, just taking derivatives and applying definitions. So it's easy to do, but it's interesting to do it yourself and see that you can recover these expressions. Okay. So next they tell us that in neutron stars, as we know, we have beta stable matter. And we have to find the relations between the chemical potentials and the densities of neutrons, protons, and electrons that we have in neutron star matter. So in this case, we are considering that in neutron stars, we have neutrons, protons, and electrons that we need them to have charge neutrality, right? So what was beta equilibrium, if we remember? That was that we had to reach the equilibrium of with respect to weak decays, and in neutron stars this is nothing else but the beta minus decay of the proton into a neutron, giving an electron and an neutrino. Okay, and this has to be in equilibrium with the electron capture by the proton to give a neutron and a neutrino. Okay. This is what is called beta equilibrium. So what is the relation that we can get from here for the chemical potentials? If we require equilibrium, this tells us that the chemical potentials for these species have to reach a relation between them. So the neutron chemical potential has to be equal to the proton chemical potential plus the electron chemical potential plus the neutrino chemical minus the neutrino chemical potential, because we have an antineutrino. Okay. But what happens in neutron stars? Do you remember with the neutrinos?
The neutrino can escape the neutron star.
Exactly.
So it should be 0.
Exactly.
I guess.
So this we can just neglect because they escape from the neutron star. We don't have them in our equilibrium any. So this just translates into this equation, this relation for the chemical potentials, right? As we saw yesterday, the neutron chemical potential has to be equal to the sum of the proton and the electron chemical potentials. Okay, so this for the chemical potentials, but what for the densities, how we can relate them? We have said also that we have to require charge neutrality in neutron star matter. Okay, so what does it mean? it means that the charge of the proton times the proton density plus the charge of the electron times the electron density, this has to be 0. So we have that our matter is neutral, okay? But the proton charge is just minus the electron charge. So the relation that we see is that the proton density has to be equal to the electron density at all densities to ensure this charge neutrality. Okay, so these are the two relations that we get for the chemical potentials and for the densities of protons, neutrons, and electrons. Is it clear? Okay, so next it tells us if the chemical potential of the electron in the ultra-relativistic limit is given by this expression here, okay, where this is the electron density. It asks us to use the previous relations that we have obtained for beta stable matter to find the relation between proton fraction and density, and to plot this function, and also for the fraction of neutrons and for the fraction of electrons. Okay. So beta stable matter has told us that the electron chemical potential has to be the difference between the neutron chemical potential and the proton chemical potential. We have computed these two quantities before, and we saw that they were very similar except for some factors. So if we take the differences of the expressions that we derived before, we see that this just takes this from here. And this has to be equal to the expression that they give us for the chemical potential of the electron in the ultra-relativistic limit. Okay. So now we can apply what? The relation between densities, okay? We have seen that this electron density, because of charge neutrality, has to be equal to proton density. So we can just substitute it. And we get this equation here in terms of the density, which is inside here of this U, and the proton fraction. And we want to plot this. We rewrite it a bit, okay? So it's kind of an equation for the proton fraction in terms of the density. It's a third order equation that we can solve analytically. But I have just used Mathematica to solve it and plot these expressions here, okay? So the proton fraction is nothing else but the proton density divided by the total density, and the neutron density, the neutron fraction is the neutron density divided by the total density. And what is the neutron density? Is the total density minus the proton density. So we can also express it in terms of the proton fraction. And the electron fraction, because of charge neutrality, is also given in terms of the proton fractions. They have to be equal, basically. Okay. So what I have done is solving this equation with Mathematica. You can solve it analytically. It's a third degree equation for the proton fraction. Okay, but it's quite tough, so you can just solve it with numerically or whatever you like, and using these parameters that we were given in the exercise. Okay, so the saturation density is 0.16 fermis to the -3. The energy saturation density is this value here, and we also are given, we will also need the value of gamma. And we will also need to remember that H bar C, we can use it to change the units, okay? Because we see the proton fraction is dimensionless, but this term here, if we see that has units of S0, which is MeV to the third divided by density, this -1 here. So we have units of MeV to the third times Fermi to the third. We need to divide by the h bar c to the third power to get dimensionless term. Okay, and we will get the right units of everything. And with this, we can just compute the neutron fraction and the electron fraction as this. Okay, and if I do that with Mathematica, I get these plots here. Okay, for the proton fraction, the neutron fraction, and the electron fraction as a function of the density, I plotted it up to third times saturation density. Okay, this would be the density that we have in nuclei. Okay, it's 1 times saturation density. This is the density in nuclei, but this is in neutron stars. Okay, so what do we see? That the fraction of protons is very, very small. Okay, and that it's almost 96% it's neutrons. Okay, and we also see that because we have to conserve baryon density, that proton fraction and neutron fraction at every density has to be equal to 1, the sum of both. Okay. And because of charge neutrality, we see that for the electron fraction, we get exactly the same amount of electrons and protons at each density. Okay, yes, because it's what we need to ensure charge neutrality. Okay. So we have a bit more time. So I'm asking, okay, so can we use this parameterization for the equation of state that we saw that the parameters have been fitted to reproduce some certain quantities, okay? But can we just plot it for different values of delta, for example, for, well, 0.1, 0.2, and 0.3 and see the differences between them? So I just took the expressions that we obtained in the previous exercises for the nuclear for the energy density and the pressure, and I plotted them as a function of the baryonic density for different values of deltas. Okay, and I see that up to 3 times saturation density, the difference is very small. But later, when you go to larger densities, and these densities are reached inside neutron stars for sure, I can see that there are some differences. And I wanted to ask you, so for which value of delta the equation of state is stiffer, and for which value is softer? Can anyone tell me what stiff and soft means for the equation of state? No? Okay, so stiff means that we have a larger energy density and pressure with increasing density. So for 0.1, the DS equation of state is stiffer than the other two. And the green one for delta equal to 0.3, this one is the softer of the 3. Okay. So we saw with Laura yesterday that it was other kind of equation of state and different degrees of freedom. Here, what we are doing is just changing a parameter of the parameterization. But we saw yesterday that a softening can also happen when you include further degrees of freedom, such as hyperons in your equation of state. And this was a problem then for, well, let's go to the other question that I wanted to tell you. For which value of delta the solution of the TOB equations will give a larger mass? Okay, so once you are given the equation of state is basically the relation of the energy density and the pressure as a function of density. This is the equation of state. This is obtained with a simple parameterization, but there are many models that you can use to obtain the equation of state, with which then you can solve the TOV equations of general relativity and get for each, if you take each of these points here to be the central energy density of your star, then you can solve TOV and get a mass radius relation, okay? So I'm asking which one of these equations will give you a larger possible mass for your mass radius relation?
I think it's for the 0.1.
Exactly.
Since it's stiffer.
Exactly. When you have stiffer equations of state, then you can have larger mass radius relations. That's why, for example, the inclusion of hyperons in your models that softens your equation of state, this can be a problem, because then sometimes you cannot reach these two solar masses that are an observational constraint. Okay. Do you have any questions relating to these or to the other parts of the problems that we have solved? Okay, otherwise, I think that's all what I wanted to do today here. If you don't have any questions, I guess then everything is clear. So maybe we can finish here for today.
Okay, Gloria, thank you. I don't see questions, comments. There have been already a few. Okay. Thank you, Gloria. We will see you again. I don't remember.
On Friday.
On Friday morning. Very good. Thanks.
Thanks
Okay.
a lot.
And I don't know, Andrea. I leave you share the section.
Okay. So I think we can restart at 11 with Peter giving his lecture. Is it fine for you?
Yeah, absolutely.
Okay.
So from my side, that's absolutely fine.
So you can start sharing your slides so that we can check whether everything works.
Yeah, just a second. Just need to set up my tablet real quick. Oh. Let me share my screen. So can you see my screen now?
Yes, so we can see
See
your
if I can...
whiteboard.
Yeah, exactly. Just let me see if I can write something.
Yes, perfect. Very good.
Okay, good.
So we start in 6 minutes.
All right, great. And I'm just grabbing something to drink real quick and be back by 11.